And we're back. Welcome back from Thanksgiving weekend and happy Tuesday. Today we will pivot a little bit in our last module for the semester, namely file system interface. And as usual, before we do so, we will have some administrative bits. The reading, the last piece of reading is sections 13.1 through 13.4, pages 529 to 554. Not a lot, but fairly lightweight reading relative to everything else we've been doing this semester, including today. That's two class meetings left. So after today, one class meeting. The morning of the 2nd of December, on Wednesday, I will be upgrading my internet and I will not be online for the first half of the day from about 8 a.m. till noon. So I will not be reachable during that period of time on Wednesday, the 2nd of December, from 8 a.m. till noon, getting a blazingly fast network connection upgrade at the home office. Last day of classes will be Thursday, the 3rd of December. The reading day will be Friday, the 4th of December. Our scheduled final exam period will be the 10th of December. That's a Thursday from 10:30 a.m. to 12:30 p.m., during which you'll be doing your project presentations. The final project is up as of Monday, November 29th, November 30th. Actually, it was up Sunday, the 29th, at late at night. But nonetheless, the final project is up, and it concerns file system implementation. Should be pretty interesting. The last day of finals, the final project will be due. That's the code, the prototype, and the report accompanying it. That will be due on the 11th of December. That's Friday at 8 p.m. I may extend that to midnight. We'll see what happens. Okay, so the objective of this last module is to look at the function of a file system, to describe interfaces to a file system, to look at the design trade-offs, things like file locking and directory structures, and to look at file system protection. So let's take a look at the file system concept. So what is a file system? A file system, contiguous logical address space. Now, of course, when we talked about virtual memory, we talked about logical address space for memory from the perspective of a process, which is a program in execution. And we looked at how the operating system manages and maps that onto the physical address space as it would appear in RAM. And so the similar concept happens with a file system. A file is a contiguous tape or array of data, and that data is laid out in some fashion on the physical disk. Now, this logical address space consists of offset 0 through some maximum offset within this contiguous array of bytes of data. And when you increment through this contiguous array or pass through it or iterate through it, you don't have to worry, but the operating system maps these blocks that you traverse in your logical address space for the file onto some disk. And so file system management is the accounting and the allocation of those disk resources as needed whenever you create a file, delete a file, move a file, etc. And so this contiguous logical address space is what a file consists of, and it is a file. And there are different types of files. You can have data files with things like characters, ASCII characters, numeric data, binary data. You can actually have program files, executable in a particular format. And the contents of that file is defined by the person that creates that file. There are many different types of files. You can have text files, you can have program source code files, you can have executable files, all sorts of things. And so files have various meta information attributes that is important to describing more aspects about the file, things like the name. And so the name of the file is really for human consumption that helps us to more easily identify it. And it's typically in human readable form. That's for our benefit. And then there's typically an identifier for the file, which is a unique number, and it describes that file uniquely within the file system. Well, certainly the operating system only cares about the identifier. The name associated with the identifier is really just for our benefit, but the operating system is perfectly happy with the file identifier or file ID. And then some different systems need what's called a file type. And that file type gives a nod to what kind of information or purpose that file has, and that's useful when you're trying to associate, in particular, applications with that particular file. Then there's the location of the file, and there's typically a pointer to the file location on the device. You need to know where on the device that file information resides so that you can retrieve it, you being the operating system. Then you also need the file size. That talks about the amount of information and protections, who can access that file in certain ways, who can read it, who can write it, who can execute it. Then you also have things like user information, the time and the date, and that's typically for protection, who's allowed to access it under what circumstances. And then there's information about the file is kept in so-called directory structure. And this directory is a type of catalog or index, if you will, of files, and the directory itself is also maintained on disk. So you have two types of data structures, as it were. You have the file, and then you have the directory that lists the names of all the files that are also on the disk. And the directory is a special type of file that but also resides on disk. And so there are all sorts of variations, including extended file attributes, things that do error checking and localization into different language, all sorts of things. And all this information is kept in the directory structure. So these directories can get quite complex beyond just a simple list of all the files available. And so on Mac OS product, when you select a file, you click on it, you highlight it, and then you enter from the menu choice file get info. It's showing you all the file information, these file attributes associated with files. And a dialog box like the following pops up. And if you direct your attention to the bottom part of this interface, you'll see some names of people and groups, and they have privileges, the operations they can perform. You also see things like the location of the file in the directory structure. You see the size of the file, and you see the type of the file. And so this is just a graphical depiction of some of that same information we talked about, this file attribute information. It's useful for describing things about the file that are generally helpful. And you'll notice here one of the things that happens on Mac OS X, based on the extension on the end of the file, it can associate that file with a program that you use to open and manipulate that file. That's a very useful thing to do. And so what type of operations would you do on a file? Well, it's certainly an abstract data type. It's a logical construct with a logical offset-based addressing approach for these one-dimensional array of blocks in which you write data. A file is an abstract data type, so you can create a file. You need to be able to write to a file. And when you write to a file, you need to identify where in the file that you're going to write. And so typically you need a write pointer location that represents where or what offset in the file you're currently going to write at. Now, sometimes in the literature, this is called the file cursor. And in fact, when I was first taking operating systems, they called it a file cursor. But it's still in some circles called a file cursor. They certainly use file cursor, or rather cursor, in databases still today, but it's less so used, but it's still applicable for the purposes that we have here. Now, the reading, we also need a read pointer. We need a cursor to tell you where in the file you're currently going to read. And then you need to be able to reposition your cursor within the file, something called a seek operation. Certainly, if you can write a file, create a file, you should be able to delete a file. Now, this truncate operation is interesting. This truncate says maintain all the file information, but take all the data, zero it out, start from the beginning. You can also open a file. And what does it mean to open a file? It means that you give a file name, the ICE file, and you search through a directory, which is an index listing a list of files, for an entry with that particular name for that file. And then once you do that, you move the contents of the descriptive information for that file into memory so that you can then operate on it very quickly from the operating system. Likewise, the dual of this operation is to close, and that's to take all of that current meta information, attribute information that's currently in memory about the file, and write it out to disk. And more correctly, it writes it out to the directory structure on the disk. So if you've added information to the file, when you close the file, the updated size of that file will be on the disk directory structure that maintains information about that particular file. And so you need all these operations on a file, this logical construct. And so several pieces of data are needed in order to manage a file that's open. You need what's called an open file table, and that's going to track all the files that are open for a particular process. You're going to need a file pointer, and that's going to be a pointer cursor to the last read-write location for each process that has the file open. Because if you're going to read or write, you have to know read from where or write to where. You also need a file open count, because if multiple processes can open multiple files, you need to know how many open files that particular block or logical construct on disk has, how many processes it has requesting to either read or write information. And so this file open count is a counter of the number of times a file is open in order to allow the proper removal of data from that file table whenever the last process closes it. And so that's sort of a reference count so that you know how many programs need this file so that finally when you close it, the physical close happens. It's taken out of consideration. You also need the disk location of the file and, of course, a cache of the data access for the information. And so you need to know where on disk the file exists, because ultimately, to make the access to this file fast, you're going to load it from the disk platters onto a disk cache to speed it up. And you also need to have access rights per process granularity, so you know who can do what on this file. So file locking, some operating systems provide locking for your files, and this is similar to reader-writer locks that we talked about when we described them in synchronization. The reader-writer lock, you can have multiple readers just reading that file if it's only read operation. You're not changing any information, but if someone wants to write, then no one else can access it. It's exclusive for the writer, but shared if everyone's just reading. And so the shared lock is similar to read lock. You can have several processes that can acquire this file, reading from it concurrently. And then you have an exclusive lock, similar to writer lock. And this is on your locking system for files. Now, that is provided by some operating systems. It's not always the case, but this is immensely useful for mediating access to the file. Now, of course, this lock can either be mandatory or advisory. If it's mandatory, access is either granted or denied depending on the locks held and requested, or it can be advisory, allowing processes to find out the status of locks, and then the process code decides what to do. It could either honor that status if it knows someone else is reading to kind of play fairly, so to speak, or ignore it and access the file anyways if someone's in the middle of writing that file. And so the advisory is participatory. And so the locking example, there are several locking examples, and in the book, they give you a Java locking example, and this is specifically from the Java NIO package, which is for your non-blocking or asynchronous IO packages or libraries. And what this asynchronous IO covers is it has something called a buffer, and a buffer holds data, and then it has your IO device. It can either source or sync data, and then you have this thing in between called the channel. And the channel is a bidirectional construct that allows you to read data from your IO device. So read is in this direction from your IO device to write data into the buffer, or to write something to the IO device. So write, from the perspective of your memory buffer, is going to be a read operation from the data's perspective. So a write takes data from your buffer, sends it to the IO device. A read for your channel takes data from the IO device and sends it into the buffer. And so the reason why this is asynchronous, this channel facilitates it, is that you're not blocking directly when you go to the IO device. You programmatically, you interact through the channel. And so as the channel mediates this transfer of data to and from the buffer with respect to some IO device, like a disk or computer network, this channel also makes available certain meta information. You can perform things like locking. And so in this locking example for Java, and I direct you to look up the NIO Java package information. There's a lot about it on the internet. This locking example is going to use the locking ability from the channel that's available in NIO package. And so there are two types of locks. There's exclusive and there's shared. And they're going to start out as shared being true and exclusive being false. And we start out and we create a random access file. So this random access file is going to be a text file, and the permissions are going to be readable, writable. And we take this random access file and we're going to get the channel for it. And now that we have this channel, we're going to create an exclusive lock. We're going to say lock from 0 to the halfway point, the length of that random access file divided by 2. And we're going to lock that portion of it as an exclusive lock. So what that means then is for that random access file, here's my random access file on disk. And what I'm going to do through that channel is I'm going to say, okay, for the first half of this logical address for this random access file, I'm going to make it exclusive so only I can write or read that first half of the file. And so after that, I would then insert some code to modify the data. Then I release that exclusive lock. And so next then, I can take the second half of my random access file. So when I lock, I say, here's the starting location, here's the ending location. There's my start, there's my end. When I did it previously for exclusive, I started out at 0, that's my start of 0, and my end, which is the length divided by 2 for that random access file. And so I do a shared lock now for the second half of this random access file. And now I can read the data, and any other process that acquires this shared lock can also read the data at the same time. So once I'm done with it, I release the lock, and then I continue on. Now, of course, programmatically, I process my standard exceptions in Java if there's some IO error, and then this finally clause is a guarantee that should all else fail, when this block exits for my routine, that I'm going to guarantee that I clean up appropriately, which is to release the exclusive lock and release the shared lock. So this is an example of locking, and this locking can be achieved using the channel infrastructure for non-blocking IO APIs or NIO package information within Java. Okay. So let's take a look at file types. I alluded to before when we looked at the file status information, that dialog box in macOS, that a file can be associated with an application. And there are all sorts of file types, and typically the easy way to determine a file type is to include information about that file in the name. And so a file typically has the file name in text, and it's followed by a period or a dot, followed by an extension. And that extension is typically a character string. It could be a few characters, 3, 4, 5 characters. And the form of that extension, that dot and some name, will say something about a hint about what that file is purposed with. So, for example, executable file has a .exe, .com, .bin, or .none extension. A .o or .obj is typically a compiled file, source code file, the result of compilation. Source code usually has an extension of things like .java, .c, .asm, and that's source code for various types of sources. .bat, .sh, those are usually command line interpreter shell scripts. Text files, .txt, for example, .pdf is a portable document format binary, and that's understandable by things like Adobe Acrobat. And then we have archives like .zip and things like .mp3 and .mp4, .movie. Those are multimedia files that are coded in a particular way to have video and or sound. And so these file types are typically noted by the extension, and it's not exclusive because you could certainly name a file, an executable file, a .pdf, and it would confuse Acrobat when it tried to load it. It would try its best and say, hey, that's not formatted as a PDF properly. I can't display it, or it's corrupted. But nonetheless, an extension is an easy way to associate the format of the file with its purpose so that an application, the correct application, can be run to try to interpret the file. And so file structure can be many, many different forms. And file structure typically has something to do with the application that's going to use that file. You could have no structure, and that would be a sequence of words or bytes. You could have simple structure, like line by line, like lines of text or fixed length. You could have variable length structures. You could have a complex structure, things like formatted documents, things like a Microsoft Word document has a particular format Now, granted, Microsoft is not enthusiastic about releasing that, but you can, through the developers network, gain access to some of that kind of thing. You can have relocatable files, things where pieces can be moved around. You can actually simulate things that are relocatable and things that are formatted using special characters. So you might have a number sign to delimit where one field begins and the other ends. Now, the person who decides this is twofold. It's the operating system, because that's responsible for file formats, executing or carrying out the file formats, as well as the programs themselves, because these different formats are understandable specifically by different pieces of software. So let's take a look at the access methods. And so a sequential access file looks like one contiguous array of blocks and bytes. And a sequential access file has a beginning and it has an end. And it also has this cursor, which defines the current position within the file. And so whenever you read or write, the cursor increments, meaning it goes to the right. So if you read from its current position, it's going to auto increment. And then you're just going to read again from the next position. It increments. And each time you read or you write, it always moves one position to one block or unit in this one-dimensional array to the right. And so when you want to go back to the beginning, you have to explicitly rewind this cursor, noting your current position, back to the beginning. And then you proceed sequentially again. And so all reads and writes read a single unit from that file, and then it moves to the next unit next door. Okay, going from the beginning in the direction towards the end. Now, sequential access has a number of methods. There's the read next and the write next. And there's also a reset. Reset goes back or rewinds to the beginning. And there's no read that occurs after the last write. And the reason for that is if you write to the last block, well, there's no read because you've reached the end and you have to reset back to the beginning again. There's another type of access method. This is called direct access. And with direct access, the file is fixed length with a bunch of logical records. So in that case, in the direct, we format our file into standardized units, and these units are logical records. So that might be my first record, my second record, and so forth, up to some nth record. And because they are standard sizes, well, now you can access in whatever sequence you want. You don't have to go from one to the next to the next to the next in order from the beginning to the end, which is what you're required to do in sequential access. With direct access, you can just say, go to a particular, read a particular record, read the second record, okay, read the n minus one record, read something in the middle, for example. So when you do a read for direct access, you say read and you give it the record number. And when you do a write, you say write and you give it the record number, and it seeks or positions to a particular location, a particular record, because they're standard size. It knows for the number of that for that record or associated with the record, it knows where to position the cursor within that file. And so you would position to some location n within that array of blocks of standard size, these records. You'd read the next one, then you'd write the next one, and you might even rewrite. And so this n here is the relative block number, and these blocks are the units more generically to describe the data structure or the record structure in your array of records for this direct access. And because these block numbers are relative, you can position your cursor arbitrarily and do a read or write anywhere instead of relying on going in sequence from the beginning to the end. And so the relative block numbers allow the operating system to be able to decide where a file should be placed, specifically at some offset. All right. So you can certainly simulate sequential access using a direct access file. If you were to do a reset, you take the current position, set it to 0. So you can simulate sequential access with direct access, but vice versa is not true because sequential can't do direct access. It would be horribly inefficient. And so you read next, you'd say you'd read whatever the current position is, and then you increment the current position to the next one. Write next, you'd say write the current position, and then you'd set the current position to its location one position after it. So you increment it. And so this is a rough idea how you would do sequential access on a physical direct access file. And so there are all sorts of other access methods, and you can build them on top of certain base methods. And they generally involve the creation of an index for the file. So you're keeping a number that represents some offset within a set of locations for that file. And this index is kept in memory in order to make fast the determination of where data should be operated on, where it should be placed, or where it should be read from. Now, if you consider something like a UPC code for maybe you're selling items in a store, for example, and you have some other record of data about that item, you might want to identify the file by the UPC code, and then you use that to index UPC code to index or refer to some other location on the disk where you find all the other data. Now, of course, if you have a large number of identifiers for your files through this index, the index might be too big, and a solution to that index being too big is to have a two-level index. And so suppose here you have your file, and then you have another part of your file, and then you have your index, and your index has your name, name one, name two, and in that index, it has a list of locations. You go here for that first file's data. For that second file's data, you're going to go over here, and maybe it has a certain size and a certain starting location, certain ending location. And so this index then makes it a lot easier to know where in the disk to go to find the contents for specific entries. Now, of course, if you have a lot of files, this index can grow quite large. And another way to alleviate that is to have a two-level scheme. And this two-level scheme is implemented throughout the ages by a lot of different companies, IBM, all sorts of purveyors of compute systems. And so this is an example of an index and relative file. Here we have an index, and that index has a name associated with a person, last name, and then you might have a logical record number. And so, for example, for last name Smith, it's going to have a number, and that number is going to refer to a location elsewhere within the file system. That's the logical record number. So record number 2 or record number 10. And maybe Asher is record number 23, for example. Now, in that location number 10 for Smith, you're going to have the full name, John Smith, social security number, age, and more full information. So this is called the index file, and this is called the relative file. Sometimes I call this disk that has it the index volume, and that's called the data storage volume. That's where the actual data is. And so with an index relative file, you have the index, which is a shorthand, and yet shorthand contains a location that is where on the large disk you can find the actual data. Okay. And of course, this index can exist in multiple levels. So let's take a look at the disk and the directory structure. So a directory is nothing more than a collection of data structures containing information about files. And so this might be our directory, and this is my first file, and it's nothing more, essentially, it's an index. And that index can contain the file name, as well as file attributes and other useful pieces of information. And that directory is an on-disk index. So this is going to be stored on disk alongside the actual blocks of data for the file contents themselves. And so both the directory structure and the files reside on disk in some form. And so a disk can be subdivided physically into partitions. And we said a partition is nothing more than a subset of the cylinders. And these disk partitions can be protected against failure by having redundant disks called redundant array of inexpensive disks, or RAID. And the disk or partition can be used in raw mode, meaning no file system. With no file system, it's just one contiguous array of bytes. Or it can be formatted with a file system. When it's formatted, that formatting corresponds to what I talked about with an array of standard size records associated with indices that you can use to identify those records. A volume is a storage area within a partition. So we have a partition, which is a subset of the cylinders, and a volume is one particular area of storage within a partition. And this is the volume is the part of the partition that you actually interact with. And this partition has a name, and it also has a file system. It's that file system that the partition was formatted into. And so each volume tracks with that file system info for the device, and it has a device directory or volume table. It lists all the contents of that volume. So that device directory, you can think of it as a large index that lists everything, all the files within that volume. Okay. And so you can have general purpose file systems, but there are also very many special purpose file systems. And it gets really interesting with the special purpose, things like embedded systems for autonomous cars and things like that. A lot of very interesting approaches to file systems that are beyond the scope of this class. And so this is depiction of the disk utility on my home system, my home office. I have four disk devices, and this particular volume is my main drive. It's formatted as an Apple file system, and this Apple file system has some reliability features associated with it. And if you look at it, I have 2 terabyte drive, and I'm using two of the two volumes, created two volumes on this thing. And so this other disk, that's 4 terabyte, that's my Time Machine disk, and this has a different file system. It's a Mac OS Extended Journal file system. Of course, Time Machine is the backup. It's 4 terabytes. I only have one logical volume because I'm just using it loop mode as a ring buffer, so to speak, for Time Machine. And you'll see here with my main drive, I use it pretty hard. Use about 1.5 terabytes for rendering video for the class. Okay, so this is just an example of looking at two different disk devices with different file systems. And I have a number of volumes on the first one, but no volume, just one contiguous thing on the Time Machine volume. And so this is another depiction. You can have one disk device, and on that disk device, you partition into two subsets, your cylinders, partition A and partition B, and each one is going to have a directory and file system. So this is the directory for the first subset of the cylinders, and then this is the directory structure for the second subset of the cylinders. And this is one disk. Another approach, you can have a single partition. That's kind of like my Time Machine drive, the 4 terabyte drive. You have your directory structure, and then you can have different volumes carved out or storage areas carved out of that single partition. Now, each one of these particular volumes, these disks, is going to use the same file system because you have a single directory on that partition and one single formatted file system. Okay, so what types of file systems can you have? We talk about general purpose, but systems frequently have many file systems and some many file systems, and some general, some are special purpose. Now, on Solaris, which was the operating system created by Sun Microsystems, now it's maintained by Oracle. It has all sorts of different file systems purposed with different things. There's the temp file system, which is memory-based, volatile for fast temporary storage and fast I/O. There's a traditional file system, ZFS, UFS. There's PROC, the processor file system, PROCFS, which is the kernel's interface to different process structures. And there are all sorts of file systems that are tuned especially for all kinds of purposes. And so absolutely you can have memory mapped file systems that act like a disk device, but it's actual memory, main memory that backs its storage. And so operations you can perform on a directory. In a directory, you can search for a file, you can create a file, you can delete a file, you can list a directory, you can rename a file. You can also navigate through the file system, going from one folder to a subfolder to a subfolder in your directory hierarchy. And so directory organization is typically done logically in a way to be efficient. You want to be able to locate a file quickly. For naming to be convenient for users so that two users can have the same name for a file, but it's different files. And so the same file can have different names, and also the same name can be used for different files. I also want to be able to group things together based on some logical property, like all the Java programs, all the games, and so forth. And so file systems afford all sorts of conveniences like this. So here's a very simple type of file system. It's called a single level directory. Here's your directory. It's just a list of names, and each one of these names corresponds to a record that has a reference to a block of the actual data itself. Now, of course, this makes it hard to name things and hard to group things. It's just a flat index of names, and each one of these names corresponds to a record that maintains a reference to some other location on disk, and that where that information is contained. And so this is very simple, very primitive, but if you have a lot of users and a lot of files, it does not scale very well. And so a two-level directory structure alleviates this problem of this naming, at least. And in this, you have a separate directory for each user, akin to when you log into a Unix-based system, you have a home directory. Now, when you have a separate directory for each user, the master directory for the file system has at its root level user 1, user 2, user 3, user 4. So then every subdirectory that you have is just another on-disk data structure, which is another index that is underneath or found in that area of the disk corresponding to that master directory entry called user 1. And so in user 1, that's going to be a directory entry, and it's going to point to a block on disk that has another directory index, which is going to have arbitrary data files associated with the names underneath there. So then in that particular case, both user 1 and user 4, for example, can have a file name called A, because at the end of the day, it's not reachable directly because you have to go through the user 1 directory before you can get to that file A. Likewise, you have to go through the user 4 directory before you can get to that file A in that next directory level. And so this gives you the idea of so-called path names. You have a set of directories, so user 1, and then the next directory, A, to get to that file associated with A. And so in that user 1 directory, that file A exists. Inside the user 4 directory, that file A also exists. But now you notice, because they exist in different directories, these paths to get to those files are different, and therefore we include the notion of a path, that set of directories you traverse in order to get to the file, in the name of that file. And so this first version of A isn't just A, it's user 1A inside user 1 directory, and user 4A, that A inside of user 4 directory. And so in doing so, with this two-level directory structure, you introduce the idea of path names, and you can have the same file name for different users. This makes it easier to search because you can begin at different places in the directory, different parts of the directory, but it doesn't give you grouping capability universally across your system. And so we have also a tree structured directory, and this extends the two-level directory structure concepts so you can have an arbitrary height tree. In the two-level, we had our master directory, and then we had our user directories. Now, if we extend this and have arbitrary directory entries that we can have as files on disk, well, then you can have arbitrary heights of this tree. So you allow, in doing so, allow your users to create directories. In this case, those user-created directories are called your subdirectories. And this gives you very efficient searching and grouping capability because you can arbitrarily put things for different purposes in a subdirectory of your choosing. And so this also includes the notion of a current directory. It's the directory you're currently referring to, i.e. which directory you've opened in order to try to find a file within your file system. And so the current directory, or sometimes the present working directory, or the current working directory, is where you are kind of like a cursor, but into the file system versus a cursor into a file. And so if you were to change directory to spell subdirectory mail, subdirectory program, and then you type or list out the word list, it's going to give you the contents of that file in that working directory. So by saying change directory, your current working directory is now the spell directory, subdirectory mail, subdirectory program. And so this idea of current working directory is another construct introduced when you allow people to create arbitrary subdirectories. Therefore, this tree can have multiple levels. You can have a directory inside of a directory inside of a directory. And so this is an example, and this schematic is in the book, of a tree structured directory. We have the highest part, or the top of your directory structure, called the root of your file system. And then you create some directories here. So there's my root directory, and we create a subdirectory called spell. Inside of that is another directory, and it has 3 entries: stat, mail, and dist, and they each point to different things. So stat is a file that points to data, dist is a file that points to data, but mail is a directory, and it points to a data structure on disk, which is another index, another directory. So that's a subdirectory. Mail is the mail directory. So that mail directory has some other subdirectories. It has a program subdirectory, copy subdirectory, print subdirectory, and an exp, that's a file. And so here in this tree structure, because you can create subdirectories, a subdirectory is nothing more than a special type of file on disk that happens to be the contents of another directory structure, another index. Okay. And so with this tree structure directory concept, you can have arbitrary height trees, not just two level, and you can also have subdirectories and introduce this idea of current working directory. And so for this tree structure, you can have two types of path to get to a file name. One is called absolute, and that's starting from the root of the file system. And so with this absolute, you always start, for example, if you want to look at this stat, you'd say slash is the root, spell, and then inside spell, the stat file. If you're going to access mail exp, absolute, you'd say on the root, you'd say spell, you would say mail, and then inside mail, the file called exp. And that's an absolute directory. Absolute directory or absolute path starts from the root file system. Relative is from the current working directory. So this says start at the root of the file system. Relatives, the start at the current working directory. And so whenever you create a file, it's always done in the current directory. If you're going to delete a file, you say remove, and the file name is done from whatever the current working directory is. That's the context for the command. The context is always at the cursor, right, the current place where you are. When you create a new subdirectory, it's always also done in the current directory. If you're in the current directory /mail, and you say make directory count, you're making a subdirectory. Inside of the mail directory, you're going to add a new entry called count, and that's going to be a subdirectory. So that count is going to be associated with yet another index on disk. But if you delete this mail directory, you're going to delete the entire subtree within your file system associated with this tree structure directory concept. Okay, so there's another type of graph you can have for directories. One is called a cyclic graph directory. And this allows you to have shared subdirectories and shared files. And this is a perfect example. So here's my root directory. And inside root directory, I have two subdirectories, dict and spell. Here are the indices for dict, and here's the directory index spell. Now, of course, I have a count file that goes to some object out of the dict directory on root, and out of the spell directory, I have a count file that also points to the same blocks on disk. So it's the same physical data on disk, but I can refer to it using two different paths. And so with this acyclic graph, typically you have something called a link. And a link is nothing more than an alias, a type of secondary pointer to an existing file. And so this link is a really powerful concept that you see on Unixes all the time. And it allows you, for example, to swap in and swap out standard Java JDKs on your installation. And so you might have user bin Java, and that user bin Java is a link to user local Java JDK 1.8, for example, bin Java. And so this link is going to refer to that particular path. And so links are very powerful because it allows you, let's say you upgraded your Java to say JDK 1.9 bin Java, right? You can update that link, and then all of your tools that use user bin Java, they do not change. So these links are a very powerful feature in operating systems. Most Unixes have links. There are two types of links. One's called a hard link, one's called a soft link. I'll leave it up to you to look up what is a hard link and what is a soft link on most Unixes. And so there are two different types of names you can have. You can have the actual file name, and then you can have a reference to that file. And that reference to the file is called a link. And there are two types of link, hard link and soft links. And so a link is another name to an existing file, and you can resolve the link by following the pointer in order to locate the file. And so if the dict deletes its list, you're left with a dangling pointer. It's just kind of left out there, right? You want to make sure that you can resolve these things. And so links are one way of doing that. You have a reference to it. And so you can also have a general graph-based directory. And so in this, of course, we start with our root directory, and there's our directory index containing file system objects. And a file system object, which is another synonym you'll see, can either be a file or a directory. And a directory is nothing more than a special type of file that contains index information. And so here we have an entry, and it points to a location on disk that has a directory or another index. And that index contains reference to a file, another reference to a file, reference to another index, or rather to another file. And then here, this is a reference to another index. And now you'll notice here, one of the things you could do, you refer down to this index, and then this could have an entry that refers back to that index. There's a cycle there. That could be a little bit tricky. And so how do you guarantee that there are no cycles if you have arbitrary graphs? You only allow for links to files, but not to subdirectories. So when you create a link has to be to a file, but not to a subdirectory. And that alleviates this issue potentially of having links. And you can also include garbage collection, right? If you're going to remove something, you don't remove it until there are no links pointed to it. So every time a new link is added, use cycle detection algorithm to determine whether it's okay to have that link. And you have the system check and say, hey, that's not allowed or that is allowed. So let's look a little bit lastly at protection. And so files have creators, and these creators of the file, one who creates the file, starts writing to it, is typically the owner. Now the owner should be able to control, since you created the file or initiated the data in that file, what can be done to it and who can do that operation to it. So the types of access to a file include reading the file, writing the file, executing the file, appending to the file, deleting the file, and listing the contents of the file. And so in most Unixes, mode of access talks about read, write, and execute operations. And there are three classes of users on Linux. There's the owner of the file. There's a collection or set of owners called a group. And then there's everyone else, which is the public, sometimes called the universe, which are all the other users that are not in that particular set or groups or that owner that created the file. Now, of course, when you have so-called file permissions, these file permissions determine whether or not you're going to turn on or off, 1 or 0, the readability, on or off, 1 or 0, the writability, on or off, 1 or 0, the executability. And so the read, the write, and execute are in that order, and they're controlled as bits. And so if you have the owner can read, write, and execute, you can have 111, and you interpret those binary values as if they were base 10, decimal, and that would be a 7. If you had, for example, group access, could read, write, but no execute, that would be 1 for read, 1 for write, 0 for execute, that would be 110, which is 6 in base 10. So it would be a group access of 6. And then public access, which is universe, if it was only execute, not read and write, you'd have the read bit is set to 0, write bit is set to 0, execute bit set to 1. That would be 001, which in base 10 is 1. So therefore, if you're going to set the permissions for some file name called game, for example, you would want to change the access or access privileges or chmod, change the access or modification control bits of this file game to be 761. Now 7 represents the owner privileges because it's the first decimal. 6 represents the group privileges because it's the second decimal, and 1 represents the universe because it is the third decimal. So then these decimals are decomposed into binary in terms of read, write, execute, and that's how you set the modification or access privileges for a file on your file system. You can also attach a group to a file. You define a group to have a bunch of usernames, and you then could change the group of a particular file, game, to be a particular group. And so change group to G that game file. And it then would adopt all of the users in that group called G would be able to perform whatever privileges would be able to perform. Then all of the users in that group would be able to perform the access privileges associated with that group field, which in this case is 110, which is 6, or read and write, but no execute. Okay. And so in a typical directory listing for Unix, you can do an ls -l for long listing, and it'll give you something like this. Now you notice that some of these entries are directories and some of these entries are files. For those entries that are files, you have a leading dash. For those that are directories, you have a leading D. And then you'll have read, write, execute, read, write, execute, read, write, execute for the user, for the group, and for public or universe. And so here we have this group, this file called intro.ts. It's a PostScript file because of that extension .ts. Read, write, execute. So the user for PostScript is 110. So you can read or write the user, and the username is PBG. The group is read, write, nothing. So it's 110, no execute. That means anyone in that staff group can read or write, but not execute this intro.ts. And then everyone else can read, but they can't write and they can't execute. So we have read, write, execute, read, write, execute, read, write, execute. So, and the user is PBG, and the group is staff. Okay, so this is an example of a listing in Unix. And then we have the same thing with directories. Now you notice here, the user can read, write, or execute this directory called private. Well, it's private, so you don't want anyone in the group to be able to read it, write it, or execute. So here that's 000, and then no one else 000. So that private group, the only person or user identity that can even examine this thing is PBG, which is the owner, right? So this is an example of Unix-based permissions using these access control bits for user, group, and universe, using those read, write, execute modification bits, and you can arbitrarily change it. You, as the creator of the file, owner of the file, you can do a change mod, a ch mod, to change the access privileges, change the access or modify the access control privileges for a particular file system resource, be that your file or your directory. And this is an example of that in Unix. All right, so if you were to go onto Windows, you'd see something like this. If you look at file properties, you see something similar, only it's a lot more user-friendly because it presents an interface. Here you see all the group names and usernames associated with that file called list.panel. It gives you the absolute path to that file system object. It's a file, listpanel.java, in on the H volume, data, patterns, materials, source, listpanel.java. And we see that all the permissions, we have full control, are denied. And it says who is allowed control, and it has the actual permissions for guests. Now that you've highlighted guests, if you highlighted Gregory Ganshi, it would show you all the permissions for that user. And so this is the same as what you'd see in a Linux system, only it presents a nice interface to make it a little bit friendlier. So that's all I had to say. And with that, we are finished for the semester with material on file system. I went over file system information as a motivation for what we're going to do on Thursday when we go over the file system project in great detail on Thursday. And so this file system is a flat file system, and you will be responsible for doing the block allocation, the writing of the file, as well as the block deallocation for a file system with a standardized data structure, record structure for the blocks on disk. So with that, we will end there. And as always, please stay healthy, please stay safe, and I'll see you all on Thursday.